All right, the last thing we're going to talk about here in the waves and oscillations unit is music. So almost all musical instruments consist of one of two things. They're either a vibrating string or a vibrating column of air. Drums are slightly different. They're usually considered to be a vibrating membrane. But any musical instrument is going to be something vibrating. That's what ultimately generates those sound waves in air. And so what we have, and the way we're really going to analyze this and apply this, is for any given string or pipe, that's what we're going to focus on, only certain frequencies can be produced, okay? And the frequencies that can be produced are the resonant frequencies for that particular string or pipe. Now keep in mind that those resonant frequencies exist when we have standing waves. So we've talked about standing waves before. As a refresher, that's those situations where the waves fit nicely into a given length for the string or the pipe, and we end up with these steady states where these waves are just oscillating back and forth, but it's a steady, consistent wave. All right. So in all these cases, we're generating standing waves within our string, within our pipe. Okay. And the resonant frequencies are the ones which ultimately generate those standing waves, and that's what we hear when we play that particular musical note. So what ultimately affects the resonant frequency, there's really two things. The first thing is the ends of the string or pipe. We talked about how for a fixed end, okay, when our wave comes in, if it hits a fixed end, when it reflects, it is flipped over and it reflects back the other way. If we have a free to oscillate end, okay, when our wave comes in, if our end is free to oscillate, when it reflects off of the end, it will go back the same way, okay, so it'll be on the same side. So that's one thing that affects what resonant frequencies we hear, the end behavior of our string or pipe. And the other thing that affects it is the length, okay? Because those waves have to fit nicely into the given space, if we change the length, that changes which waves fit nicely. If you think about any musical instrument, basically all of them change their frequency, change the note that you play by changing the length, okay? The trombone's a really nice example, okay? By extending that horn out or back, you change the length. With guitar strings, with violin strings, you place your fingers at different positions to change the length of the string that's vibrating, and that ultimately changes the note. But changing the length is really the key for almost all of these instruments. That's what ultimately changes the note that is played. So we're going to actually start doing some math here with standing waves and resonance. So mathematically, we can figure out what wavelengths will produce standing waves in a given length for a pipe or a string. And there's two possible cases, one where both ends are fixed or both ends of the pipe are open, or if both ends are free to move, meaning both ends of the pipe are closed. Okay, so we're going to refer to this as the open or closed case. Okay, basically meaning that the two ends are identical. All right, and when that happens, this equation here tells us what wavelengths will fit nicely into that space. All right. So I think this is easiest to think about visually. So I'm going to start here with this closed pipe where we have a standing wave set up. And if we look at that standing wave, which goes from here to here, that represents half a wavelength, right? The full wavelength would go on back down. So this is half of a wavelength. And that generates a standing wave. That fits nicely into that space. The next one we get here, we have from here to here, so that's one full wavelength. Okay, so if the length of the pipe is equal to one wavelength, that wave will fit nicely in there. And then the next one we have, there's one wavelength plus a half. All right, so there's 1.5 wavelengths or 3 halves. And if you think about this, this pattern really is half a wavelength, 2 halves, 3 halves, and so on. So this equation here allows us to solve for all the possible wavelengths that will fit nicely into this space. Okay, so what this equation says is the length of the pipe or string, all right, is equal to m, which is the harmonic number, and that basically tells us that there's multiple possible wavelengths. So this is a harmonic number of 1, this first one here. The next one is a harmonic number of 2. The next one is a harmonic number of 3. So that recognizes that there are multiple wavelengths that will generate standing waves in this given length. Okay, times the wavelength of the wave, and it's lambda sub m, once again, because there are multiple wavelengths that will work, divided by 2. Okay, so this allows us to solve for what wavelengths will fit nicely into the pipe. Okay, all the different wavelengths that will fit nicely into the pipe. All right, this first one here, when m is equal to 1, that first harmonic, we call that the fundamental frequency, and that really represents the biggest possible wavelength that can fit into this pipe. All right, and we see that visually right here. If we have a situation where both are open or both ends are fixed, we end up with the exact same relationship. All right, for that first harmonic, the length of the pipe is half a wavelength. For the second one, it's equal to 1 wavelength. For the third one, it's 3/2 times the wavelength. So we see the same pattern for both of these situations when the end behavior, the ends of the pipe or string, are the same. So the other option that we're going to have here is when one end is fixed and the other is free to move, which would be the equivalent of an open-closed pipe. In other words, the two ends are different. And so when that happens, we're going to take a look at what pattern exists. So if we look at this first harmonic here, all right, this is the wavelength that ultimately results in a standing wave, the longest possible one. And this actually ends up being just 1/4 of a wavelength, because if we continued this up to the peak, that would be half a wavelength, and then all the way back down would be a full wavelength. So this segment here is really just 1/4 of the wavelength. So when the length is 1/4 of the wavelength, we will have standing waves. The next one that we get is this one here. This is the next harmonic that exists, and that occurs when we have 3/4 of a wavelength, right? It's not quite a full wavelength. We need that little extra bit to make it a full wavelength, but we end up with 3/4 of a wavelength. All right, and then the final one here is when we have 1 full wavelength plus a little bit. All right, so that ends up being 1 1/4 or 5/4 of a wavelength. So that's the pattern that exists, okay, for open-closed pipes that are different at each end. All right, and once again, it is quantified here with this equation, L equals m lambda over 4. Two key differences here compared to the open or closed case. First of all, it's divided by 4, not divided by 2. And the second thing is m, our harmonic number, is 1, 3, 5, etc. Okay, it's really important to note that for the open-closed situation, there are no even harmonics. Okay, so we generate all these waves, but for the open-closed one, we only generate odd harmonic numbers. And that leads to this pattern here of 1/4 of the wavelength, 3/4, 5/4, etc. Okay, so we've been talking some about harmonics, and if you're not familiar with music, that's probably a new term to you. But here's the whole idea of harmonics. Whenever we play a note on a musical instrument, whether it's a string instrument, whether it's one that results from a column of air, like a trumpet or a flute or something, there's multiple different frequencies that are generated. There's multiple different resonant frequencies. And we call these different frequencies harmonics, okay? So even though you're trying to play one note, all right, and the note that you play is the fundamental frequency, that's the note that you ultimately hear, the first harmonic, okay, you end up generating additional frequencies, okay? Those are those additional harmonics. So even though you're trying to play a single note, additional harmonics are generated in the process. And this ultimately contributes to the richness of the sound. We'll talk a little bit more about that later. It is important to note, though, that the open-close only generates these odd harmonics. So when we're talking about both ends being fixed or free, we end up having all the harmonics. We have the first, the second, the third, the fourth, etc. If we're talking about an open-closed pipe, like we saw on the last slide, only the odd harmonics exist. So let's try a practice problem, because I think this may make things a little bit easier. So weights on a guitar string, which is fixed at both ends, that's a key piece to this, travel at a speed of 409.6 meters per second. If the string is 0.8 meters long, find the frequencies of the first 3 harmonics. So I'm going to start here with L equals m lambda over 2. That's my equation for when both ends are fixed, like this case. And I'm going to solve for what wavelengths will create standing waves, okay? And so for the first one, I'm going to say my length, which is 0.8, is equal to m, which is 1, times lambda, that's what I'm solving for, over 2. So the wavelength of my first harmonic is going to be 1.6 meters, okay? I can do the same thing with my second harmonic. I can say 0.8 equals m, which is now 2 times lambda over 2, which means the lambda for the second harmonic is 0.8 meters. And then I can do the same thing for the third harmonic, 0.8 equals m, which is now 3 times lambda over 2. And so the lambda for my third harmonic ends up being 0.53 repeating. Right? So I now have the wavelength for my first three harmonics, and I can use that combined with this velocity to find my frequency. So in all three cases, I'm doing the same thing to get my frequency, and that is using velocity equals wavelength times frequency. So I can say 409.6 equals 1.6 f, and so the frequency of that first harmonic is 256 hertz, which is a C note. For the second one, 409.6 equals 0.8 f, and so the frequency for the second one ends up being 512 hertz. And then my frequency for the final one, 409.6 equals 0.53 f. I end up getting a frequency there of 768 hertz. Okay. For those of you that do music stuff, this right here would be your fundamental frequency. This would be the octave, okay? And then this would be what is referred to as the fifth, I believe. So we have the fundamental, the octave, and the fifth. And you guys know that you can produce all of those notes, all right, on the same string, right? So what this really shows us is that on this particular guitar string, okay, we generate one frequency, 256. That's our fundamental frequency. That's the note that we actually hear. But in addition to that, we're going to generate a note of 512 hertz. That's the second harmonic. And a note of 768 hertz. That's the third harmonic. And all three of those are going to combine using superposition to create the sound that we ultimately hear. Now the second question here is the first three harmonics on a different string are not the same frequency, even though the length of the string is the same, and we want to explain why that's true. Okay, and the reason is the velocity of the waves on that string are not going to be the same. All right, so when we have a different string, that means that the velocity of the waves on that string are not the same, and that ultimately results in different frequencies, even though the lengths are the same. All right, for this problem, we have an organ which acts as an open-closed tube. We know that that's important here. And we want to know what is the length of an organ pipe that is designed to play a C note with a frequency of 128 hertz. So the first thing I'm going to do here is I'm going to find my wavelength using velocity equals wavelength times frequency. And at first you might think that we don't have the velocity, but we actually do here. Whenever we're dealing with a wind instrument or a pipe, the velocity of the wave traveling through that pipe is simply the speed of sound in air. So 343 meters per second, and that's going to be equal to my wavelength times my frequency. And so when I go ahead and solve for my wavelength there, I get a wavelength of 2.68 meters. Now that I have that, I can use that combined with my equation for an open-closed pipe, m lambda over 4, to solve for my length. So my length is what I'm looking for. I'm going to leave that as L. M, in this case, is going to be 1. The note that we hear, okay, is always the fundamental frequency, okay, when m equals 1. So whenever you're hearing a note, you're hearing the frequency of the fundamental. Those additional frequencies, those additional harmonics, just add complexity to the note. So it's going to be 1 times 2.68, the wavelength, divided by 4. And so I end up finding that the length of the pipe here that will produce this note is 0.67 meters long. We've touched on this a little bit thus far, but whenever we play a note on any instrument, we produce more than one frequency. We produce multiple harmonics, okay? So what does this do ultimately to the wave produced? Okay, so let's take a look. So here we see 3 different waves being produced, the fundamental frequency here for some instrument, and 2 additional harmonics, okay? Those 3 waves all combine, they all undergo superposition, and ultimately produce that composite wave that we see here down at the bottom. Okay, those 3 combine to produce that composite wave. And there could obviously be more harmonics than just 3, but we're just looking at 3 in this case. One really important thing to note about that composite wave is if we look at when that wave starts repeating itself, okay, it's at these points here, all right, and those ultimately match up with when the fundamental frequency starts repeating itself, okay? And that's why we say that the note you hear is the fundamental frequency, because the frequency of the composite wave is the same as the frequency of the fundamental frequency. These harmonics here simply add complexity to the wave itself. So as we just said on the last slide, musical notes end up being complex waveforms. They end up not being a nice simple sine wave. They end up representing the superposition of many different waves, of all the different harmonics. All right. We hear, though, the fundamental frequency. All right. So even though those harmonics exist and add complexity to the wave, we still only hear the frequency, the pitch of the fundamental frequency. This idea of harmonics helps us to explain why two instruments can play the exact same note yet still sound different. So we see here what the waveform looks like, and I don't know how accurate this is exactly, but what the waveform looks like for a piano playing a C note versus a clarinet playing a C note. We notice that the waves repeat themselves at the same intervals, which means they have the same frequency. However, clearly these two waves look different, okay? And that's why these two instruments can play the exact same note, have the exact same frequency and pitch, but the actual sound of the wave is different. And those differences result from how those harmonics are added together, okay? Each different harmonic might have a different amplitude, might affect the final wave a slightly different amount, and that's why we can have a different looking wave for two instruments playing the exact same note. All right, so the last thing we're going to talk about here, and this is purely going to be a conceptual thing, is the idea of beats, okay? So beats is a way that musicians will sometimes tune their instruments, but what a beat is basically when two frequencies are played that are close but not the same, okay? So they're it's not like harmonics where it produces a very nice, rich sound. This is like two frequencies, like maybe we have 440 hertz, okay, and 446 hertz. So they're very close, all right, but they're not exactly the same. And what it ends up producing is a quite unpleasant sound. So I'm going to go ahead and demonstrate what exactly this sounds like here. All right. So first I'm going to play this 440 hertz sound. And so there's that tone there, 440 hertz. And now I'm also going to simultaneously play 446. And it's going to make a very unpleasant sound here. So you can hear, as it's going through, there's like a wah, 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 wah sound, okay, when the two frequencies are played that are close but not the same. So let's take a look visually at why exactly this happens. So here we have a picture showing the two frequencies. One is in red here, and the other is in blue. And those two frequencies combine to form this composite wave. And so we see there are points in time, okay, like right here, where the peak of one wave, or the crest, and the trough of the other wave almost exactly match up, and we end up getting destructive interference, okay? And that cancels it out, all right? That cancels out those two waves. We also have times, though, like here, where the two peaks do match up, the two crests match up, and we have constructive interference, all right? And what that leads to is a bigger wave. It amplifies it, all right? And so that composite wave has periods like this, all right, where the amplitude is very small, meaning it's quiet, and periods like this where the amplitude is quite large, meaning it's loud. And so that sound you're hearing is that fluctuation between a low amplitude for your composite wave to a high amplitude. So here's your wong, wong, okay? That's where that sound is coming from. And it all comes back to the fact that these waves are just slightly off, and so they go through these cycles, these fluctuations of having their waves match up perfectly with constructive interference and having them cancel out with destructive interference. And so the number of beats we ultimately hear, okay, ends up just being the difference in the two frequencies, all right? So if we have two tones here of 330 and 332, we would hear 2 beats, okay, because the difference in the frequency is 2. So let's take a look at what that sounds like. Okay, so there's the 330. We add in the 332. And you hear every second, wow, 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 2 beats per second. If we change that frequency, so if we make it further away from 330, we're going to start hearing more beats per second. So now we're at 334, so we should be hearing 4 beats, 4 of those wow wows per second. If we reduce it now and get it closer to 330, we can hear the number of beats slowing down until eventually those two tones are the same, and we don't hear that difference. Okay? And it's just one coherent sound.